Welcome, Mechanics of Materials students. This lecture will start our exploration of the concept of stress and then apply a very brief understanding of strain and the stress-strain relationships to give us another piece of information to apply when we have a statically indeterminate problem. So we'll be picking up several concepts in this lecture and the one to follow. But let's get started with a very important concept for mechanics of materials, and that is the concept of stress. And how is stress different than just force or load? So to do that, we'll take a look at a really simple object that's being loaded, and that's a cylinder. So with this cylinder, we've got a cross-sectional area of A, perpendicular to the cylinder's axis, and we're yanking on that cylinder with a force F. So we have to apply it to both ends, otherwise it'll accelerate. It's in static equilibrium, and it's seeing a force along its axis of F. So if we were to cut the cylinder in half and look at the N force that is parallel to the axis as if it were a beam, it would be F. Okay? So the definition of stress is force per unit cross-sectional area. Here in the notes it says per unit area. That is the area that is perpendicular to the direction of application of the force. So it would be the surface normal to the surface where that normal is in the direction of that the force is being applied. And it will have units of force per unit length squared, which just so happens to be the units of pressure. And if you think about it, if you are looking at pressure being exerted against a surface, that is a force that is per unit area. So you could get, say, the total force on some surface of a pressure vessel by just integrating that force per unit area over the area to which it's applied. So that's stress, force per unit cross-sectional area. So moving on, and again, this is a very quick snapshot of a couple of super important principles. We will definitely be returning to these in more detail, but this is just to give you an idea of the difference between load, displacement, load, elongation, and stress and strain. Okay, so we define stress. So if we think about some body that's like that cylinder that's subjected to tensile forces, it's going to stretch. Or if it were subjected to compressive forces, it would get shorter, it would compress. So the extent to which something will stretch or compress for any given amount of applied stress, that quantity is known as strain. And so the extent of stretch or extent of compression is known as strain, and it's denoted by this kind of Greek squiggly letter E, epsilon perhaps. You can look it up. Just like going back, stress is usually the Greek letter sigma, lowercase sigma. You'll see these stress and strain with those Greek letters. Strain is defined as the change in length over the original length. And this actually, I should take a step back and say this is axial strain. We will develop expressions for shear strain, which is a little bit different in later chapters. But just looking at our cylinder, we're stretching it, we're applying a tensile stress, so it's going to stretch. These are all in the axial direction along parallel to the axis of the cylinder. So we can use this definition of strain, change in length divided by original length. And so all the units disappear. Strain is a unitless quantity. Okay. So if we were to look at force versus length change, so displacement kind of related, but this time it's the change in length. You would notice that depending on the original length and depending on the cross-sectional area, we might get a different plot. So if we have a small area and a longer length, it's going to take a lot less force to give a certain length change, so we'll have a curve that's low. If we've got a big cross-sectional area and a squatty little length, it'll take a whole lot of force to give very little stretch. So the relationship between force and length change, or force and elongation, length change is sometimes referred to as elongation. This is dependent on the geometry of the body with reference to the direction of applied stress. So a short, squatty type of cylinder is definitely going to require more force for a given elongation than a long, skinny one for the same material. Now, as it turns out, there are properties of the material itself that also play into this. For instance, for the same dimension cylinder, if we applied the same force to a cylinder made of iron, it wouldn't have as much elongation as a cylinder made of rubber, for instance. So there is a material property that plays in here. But to get at that material property and look at how it affects the force versus elongation relationship, we have to have a way of getting rid of the geometric factors. And as it turns out, if we plot stress versus strain instead of load versus elongation, all of those geometric factors effectively cancel out. And we could write mathematical expressions showing that they do, and we're left with only the effects of the material properties. And so this is perhaps the stress-strain relationship for that particular cylinder, and it no longer is a function of the geometry. Something important to remember about a stress-strain plot is that for almost all materials, definitely most of things like metals that you'll frequently build structures out of, if you have small strains, the stress versus strain relationship plots in a straight line, usually straight line through the origin. And so this is known as the elastic or linear region. And most of what we will do in mechanics of materials will operate in this region. This is known as the elastic zone. And when we design structures, we typically want them to behave elastically. Once we get past that linear region, we apply too much stress or we allow it to stretch too much, those strains aren't recoverable. When we remove the load and there's no stress, the body won't go back to the same configuration it started in, unrecoverable, so it'll have permanent deformation. Those are great if we're trying to form something and change its shape permanently, but if we're designing something to be put into service, we generally do not want it doing that. So these small strain regions, this linear portion of the stress-strain curve is where we're going to operate. And so we'll leverage that quite a bit more as we go on. So moving ahead, if we take a look at that region, that linear region, and kind of focus in on how can we use force, stress, elongation, strain, and that linear relationship between them, we can create a few really simple mathematical relationships that allow us to handle some of those statically indeterminate questions that we had to kind of take a pass on in the past in statics. So let's take a little bit of a look here. If we summarize those relationships, stress, force, area, we've got stress equaling applied force divided by cross-sectional area, strain, elongation or change in length divided by a initial length. If we ratio stress and strain, we're going to get the slope of that linear area up here. We're going to get the slope of this line. And I said that was a material property. That is known as modulus. And if we're talking about an axial stress-strain relationship, this is known as the tensile modulus, compressive modulus, or Young's modulus. You can look it up in a handbook. It's dependent on temperature and material and nothing else, pretty much. So that tends to be a constant for most scenarios in which you'll design something. So we can mix and match these. We can substitute in one for another, and we can come up with an expression for modulus in terms of force, area, and initial and change of length. take out our change in length, and we are left with a relationship between force, initial length, initial cross-section area, and we're going to assume that stays constant here, which it will for these small strains that we're going to be looking at. And those are all typically givens in a problem. So if we take this expression and we look at our expression for the force of a spring with a given stretch, something that we've seen in statics before, we'll notice that this delta that we see in the spring equation is stretch or compression of the spring. Well, that's the same delta L we have here. So if we look at delta L and F, we'll notice that this L0, A, and E terms, their ratio there, if we kind of flip it around and write F in terms of delta L, we'll notice that modulus times cross-sectional area divided by initial length would be K, our spring constant, in our expression for force due to a spring that's been stretched or compressed. So we can use the fact that modulus, initial area, initial length are usually given in a problem. We can look up a modulus if we know the material. Now we know the force if we know something about how much that material stretched. So if we can use that as an additional relationship to solve statically indeterminate problems if we can somehow get at an expression for that stretch. Here's where we're going to leverage our small strains, our small deflection approximations, and do a little bit of geometric wrangling so we can deploy this additional expression to solve statically indeterminate problems. So up to this point, we've introduced definition of stress, definition of strain, both just simple axial direction relationships. We've looked at the difference between force elongation versus stress and strain, with the former being dependent on material properties and geometry, and the latter, stress and strain, only on material properties. We've looked at how we can rearrange all the variables for those three expressions and arrive at a spring constant force elongation relationship that lets us express force due to a given elongation in terms of some stuff we can probably look up or would have to know at the beginning of a problem. We have not gone into the depths of stress and strain that we will later on, stress at a point. We're merely taking the very simplest kind of manifestation of those concepts and then turning around and applying them to statically indeterminate problems. We'll dive into more details of stress and strain later, trust me. But right now we've just come out of probably our statics. We've done a little review of our statics, and so now we want to look at a way we can deploy this very simple relationship of stress and strain to solve the problems that we had to put aside in statics. Okay, so we're gonna do an example to show how we use our force equals elongation times this kind of spring constant stiffness expression, our EA over L0. So we're going to start with this weight. This is a rigid bar weight, and it's being held up by three little bars. They're all two force members. They all start out with length L. There's our initial length, and they're all the same. And they're separated by a horizontal distance of h. So we have one bar at point A, one bar at point B, one bar at point C, holding up this weight. So we want to know what the force is in each of the vertical members. And basically we're going to assume that somewhere along here somebody might tell us what the bars are made of. And we need to find this in terms of whatever the weight is, because theoretically the relationship between the forces should ratio with the weight, but presuming we haven't made the bars out of different materials, that ratio should stay the same. Okay, well, we can FBD the weight. So here's our FBD of the weight. We have its own weight. weight force pointing vertically downwards, and that's collinear with force B, and then we have forces A and C acting at the ends of the bars. So we can say the sum of the forces in the vertical direction is 0, so FA plus FB plus FC equals the weight force, and we can take the sum of the moments around this point and say, because H is the same on both sides of F, the line that goes through FB and W, we can say that force A equals force C, and that's going to keep this weight from rotating around its center of mass. Okay, we have 2 equations and 3 unknowns. Drat. Okay, so let's see if we can't use our newly minted force, elongation, and kind of stiffness expression to give us more information. So, well, we know that the original length of all of them is the same, so that's cool. So if we look at our F equals delta L times the stiffness expression, we don't know delta L, but we know L0. And presumably, if somebody has specified the bars, we would be given A. And if we know what they're made of, we can look up the modulus, so we'll have E. So everything's hinging on this delta L. So how might we use something about the geometry of the problem to get ourselves some expression for the elongation that each bar is going to undergo, no matter what they are? Now here's where I have to step back. If they were all made of the same thing and they all had the same area, we could probably make some assumptions about what delta L is going to be in each case. But at this point, we're holding it open. We don't know what they're made of. Maybe one of them's rubber and one of them's steel. So we're going to have a different modulus. Maybe one of them's really skinny and one of them's really fat and made of the same material. So right now, we can't make any assumptions about what force elongation relationship we're going to have, because we're going to have to hold that stiffness expression kind of open, because we don't know what E and A are. We only know L0. Okay. But we can say something about how things will move when they do elongate. So now we're going to actually kind of take a step back to dynamics. And if you haven't taken dynamics, we're going to do a quick review of it. This weight, this big long bar weight that's connecting all of our little hinged bars, is rigid. That means it, unlike the bars holding it up, is not deforming. It's a rigid body, which means it can translate and rotate, but it can't, bend. It can't twist. It can't extend or compress. So that means the motion of points A, B, and C, when those vertical bars stretch, if we look at the starting position of points A, B, and C, and then the final positions, they're going to have to be some combination of translation and rotation and nothing else. Okay, we don't know what the magnitudes, relative or absolute, are, but we could write an expression for what they might be, and then just solve for signs and magnitudes later on. So this is a hypothetical change. And again, this makes it look like we already know that, say, bar C is going to stretch more. That delta C could be negative, or it could be a different value versus delta A. So it could be going the other way. But we know that we could draw the motion of that bar weight W, as a motion of points A, B, and C translating downwards. So the weight translates. It doesn't rotate, so it just drops, but it hasn't spun on its center of mass. So that takes point A to A prime, B to B prime, and C to C prime. Okay. Now we're going to assume that maybe the stretch in the bars A, B, and C are different. So, okay, fine. Now we're going to add an expression that allows the stretch might be different and allows the weight to rotate. We don't know which way it's going to rotate, or if it's going to rotate at all. but we'll assume it does, and we'll leave the magnitudes and direction open and just write an expression for if it rotates at all, here's the relationship between the new positions of points A, B, and C. So we're going to assume, hypothetically, A stays in this one position, B moves down some, C moves down more. What's fixed is A prime to B double prime to C double prime has to be on a straight line. That's a rotation. So A prime to B prime to C prime, straight line, it rotated downwards about point A. So we had a translation, we dropped, now we rotated. So we can write the elongation in these vertical bars as the total change of position of point A from its starting point here to its final point here. B is the starting point up here to its final point way down here, and same with C. So now we have a constraint that everything had to stay on the straight line. That's another relationship. The fact that ABC is on a straight line, A prime, B prime, C prime is on a straight line, and A prime, B double prime, C double prime is also on a straight line. The straight line, straight line, straight line geometric relationship links delta L of A, delta L of B, and delta L of C. So it's the geometry of translation, drop, and rotation, no twist, no bend of that bottom weight that allows us to relate elongations of each of the bars to one another just geometrically. Okay, so doing that mathematically, we can say by applying that straight line relationship, we can say that the length of B to B double prime, this length here, is going to be, it's the midpoint basically of this trapezoid. So we have H. So now we're just using geometry of this sort of trapezoidal figure here of A to C prime. And we're just writing the relationship of this length here as a function of this length, and it's just the midpoint, so it's literally the average. So this B to B double prime is 1/2 of A to A prime plus C to C double prime. And of course, B to B double prime is delta B, which is its change in length. A prime to A is delta A, C double prime to C is delta C. So now we have a relationship between elongations. Okay, so we'll go back to our kind of our spring constant and remind ourselves that each of those elongations is related to the force in each of those vertical members, which was the thing we wanted to solve for in the first place, times original length, which we were given, some expression for the cross-sectional area, and the modulus of the material, which we would have to know. Okay, so we can take each of these expressions and drop them right into our geometric expression that we just derived with our translation rotation. Drop it all in. And now we have another expression, ta-da, relating forces that we needed to know. So check it out. Come up here to our statics expression, and we had 3 unknowns, force in A, force in B, force in C. We had 2 equations. We needed another equation. We used the geometry of the movement of a rigid body, our translation rotation, to relate elongations in the bars. And then we used our stress strain definition derived expressions to relate force to that elongation. And now we have another expression relating our 3 forces to go with 2 coming from statics. So now we have 3 equations and 3 unknowns, and we can solve them in terms of W and our areas and our moduli for each rod. So basically the force in B is equal to the weight minus 2 times the force in A, which is the same as the force in C. So we have them defined as a ratio. The absolute forces are going to be dependent on the magnitude of the weight, the area, and the moduli of each of the rods. So again, we have, from a design standpoint, we could have a real stiff rod with a small modulus or vice versa. And those are, as we see up here, those are linearly related here. So we could literally double one, have the other. And hence big weight savings from stiff materials if we need to design around force. Okay, we will end that here and then come back for 2 more examples that show ways to use our kind of our stiffness spring constant expression relating force and elongation via our definitions of simple axial stress and strain with some knowledge of the geometry to give us that extra equation that we need to solve statically indeterminate problems. We'll have 2 more examples in the next lecture that continue with this concept.